we've always said acids have H's and bases have OH's. And we've always said a salt is nothing more than a metal and a nonmetal combined. But we've never said anything like, oh, by the way, a salt can be an acid, or by the way, like a salt can be a base, sodium chloride. You have to ask yourself, where did the sodium come from? The sodium came from sodium hydroxide, the base. Now, is sodium hydroxide a strong base? Yes, all group 1 bases are strong. Where did the chloride come from? It came from HCl. Is HCl a strong acid? Of course it is. What did we say about their conjugates? They're both worthless. So a strong base gives off worthless conjugate acids. A strong acid gives off worthless conjugate bases. So NaCl, those are both worthless. So they have no effect on pH. Take this NaF though. Split it up. Where did the Na come from? NaOH. That's a strong base. So NaOH, the strong base, produces the conjugate acid Na, worthless. Ain't nobody got time for that. What about the fluoride? Where did the fluoride come from? The fluoride came from HF. Now, is HF a strong acid? No, it is not. HF is a weak acid. Since HF is a weak acid, it will give off fluoride ion. That fluoride ion is a relatively strong, compared to water, base. So if you just throw some fluoride ion into a solution, it'll actually have the effect of grabbing onto hydrogen, sucking up those hydrogens, and turning back into HF, because that's the way the equilibrium wants to go. So an F ion will have a basic condition around it because it's going around sucking up hydrogens. Let's look at that one more time. Hydrofluoric acid has a Ka of 6.6 times 10 to the negative fourth. So if it has a Ka of 6.6 times 10 to the negative fourth, then what is its Kb value? Kw is equal to Ka times Kb. When we do the math, we get that the Kb is equal to 1.5 times 10 to the negative 11. Well, let's compare that to what it is, not for a weak acid. Let's compare that to what it is for a strong acid. So we'll label this one HF over here. Let's go back to our table and see what was the Ka value for a really strong acid. Hydrochloric acid. How about hydrochloric acid? So we can do the math for a hydrochloric acid just like we did before. 1 times 10 to the negative 14th, Kw, is equal to the Ka, 1.3 times 10 to the 6th times Kb. What is the value for Kb for this sucker? Turns out Kb for hydrochloric acid is 7.7 times 10 to the negative 21. That's a pretty big difference. Hydrochloric acid produces a conjugate that's almost worthless. Whereas hydrofluoric acid, a weak acid, produces a conjugate base that is relatively strong compared to water. We can do the same for the rest of them as well. Where does ammonium come from? Ammonium hydroxide. That's a weak base. So a weak base gives off a relatively strong conjugate acid. Where does the chloride come from? The chloride comes from HCl. HCl is a strong acid. That means it gives off a worthless conjugate base. And then if you happen to mix the two together, it just all gets very, very scary, and we don't have to worry about that in this class. We saw this before in the table. You want a very, very polar bond because a very, very polar bond means it's super easy to lose that hydrogen ion. So you want something that's super, super polar. Very, very polar is good. And you want a very, very weak bond strength. HCl is a pretty strong acid. HI is also a strong acid. In fact, it's stronger. Why is that? Because the bond strength is so low. Why is bond strength so low? Because I is freaking huge. It's got tons and tons of layers of electrons, making that bond that holds the H to the I a fairly low bond energy, fairly low bond strength. So that just means it's going to be easy to break and release that hydrogen ion. The last thing I can talk about is the idea of, what about an oxyacid? What about HNO2 and HNO3? HClO2, HClO3, and HClO4. Turns out, as you add more oxygens for these oxyacids, that makes the acid stronger and stronger and stronger. Turns out that all you have to do is think about, oh wait, polarity. So here's a picture of HClO3 and a picture of HClO2 and HClO4. The more oxygens you add, the more electronegativity you're adding. That makes one end of the molecule crazy negative and the other end of the molecule crazy positive. Remember, greater polarity means greater strength of an acid. It's easier to lose that H. You can tell that every time we add an oxygen, we are making this a much stronger acid. We're going from a Ka of 3.5 times 10 to the negative 8 all the way up to a pKa of large.